Swayam Prabha. Digital India. Educated India.
Okay, so good morning everyone. Last class we saw this division problem and we saw an NC2 algorithm for division. So essentially the idea that we explored last time was we reduced division to the reciprocal problem, because essentially it is computing the reciprocal of an n bit number and then multiplying it with the dividend. And the way that algorithm worked is we used the Newton-Raphson's method to approximate to approximate any function, and then we saw that we can use that idea in log many iterations. We can get a n bit approximation of the reciprocal, okay, and in each iteration the way it works, we need multiplication, so it needs some log n depth. So that is why we get a NC2 algorithm. So now the question is, can we do better than NC2? I mean, of course, NC2 means log square, so can we bring down the depth below log square? Okay. So this is going to be our agenda for the next couple of lectures. So what we will prove is the following result, that division is in NC1. Okay. So this is actually a very strong result, and this is actually a quite a non-trivial result. So this was shown by three scientists, Paul Beam, Cook and Hoover. Okay. Yes, same Cook as Stephen Cook. Yeah. So he actually had he actually had a lot of work in circuit complexity as well. So he explored these bounded depth circuits, and not just this work, there are other works also that he has in circuit complexity which are quite pioneering. I don't know, so maybe we might look at some of his works later on also, but essentially the same Cook, and this result was shown in early 1980s. I think it was 83 or something like that. Yeah. So anyway, so the idea is it's actually a combination of a lot of ideas, but essentially it uses a lot of non-trivial stuff from number theory. Okay. So some of those facts, of course, we will try to prove. I will try to give you a proof of those things, but some of those we will just assume that they are true, because the proof itself is quite non-trivial. If you are interested, you can of course look up the proof from any book on number theory or even some online resources, but we'll see when we come to it. Okay. Okay, so this is going to be the agenda. So now let's try to let's try to define a few things. So first of all, just to recall, so the division problem was to formally define it, given two n bit integers x and y. Let us say we want to compute the quotient. Okay. We will also look at a few other problems. Powering. So what is the powering problem? So given an n bit integer x, compute the powers. So basically compute x to the power 0, which is nothing but 1, x to the power 1, x to the power 2, so on, let us say till x to the power n. So, we will compute the binary representations of this. Okay. And just to mention, so like for example, x to the power n. So, how many bits will x to the power n need? Okay. So, x to the power n would need in the worst case it can be as large as n square bits, okay, because x is n bits. So, we will assume that for each of these we keep a space of 2n square. Okay. So, we assume that each of these is a 2n square bit string. Okay. You can append it with zeros if it is less than that. Of course, it will be less than that. So, you append it with preceding zeros. The third problem is iterated product. So, we have seen iterated addition and we have seen single multiplication, but we will, let us call it iterated product or iterated multiplication. So, this is given n bit integers x1 to xn, let us say, we want to compute the product of all these numbers. Okay. Now, why are these problems interesting? The reason they are interesting is because what we will show is that, so of course, this is the goal, we want to compute this, but what we will show today is that these two problems are equivalent in some sense. Okay. So, it is enough to compute powering to get this, and if you look at the problem of powering an iterated product, powering is essentially a special case of iterated product, right. So, essentially if you, what we will show is that if you can solve iterated product, which means you can solve powering, and by the reduction that we will give, you can solve division also, and we will actually show reductions in the other way also. We will show that actually division also, powering also reduces to division, and this maybe later on we will show that powering also, iterated product also reduces to powering. So, that is actually quite a non-trivial thing, which says that, well, if I want to compute iterated product of n bit integers, it is enough to compute powers of some number. Okay. So, that is a little bit maybe, well, not very counterintuitive, but it is a little bit non-trivial, but we will also see that reduction later on. So, essentially the point is all these three problems are equivalent up to some notion of equivalence. So, what is that notion? So, let us define that. So, first I will define what is log space uniform. Okay. So, log space uniform NC1 So, what is log space uniform NC1? So, NC1 we have seen is the class of functions for which there are log depth circuits of bounded fan-in having polynomial size over and or and not, right. What is log space uniform? Now, suppose, so I think I briefly mentioned this also last time, that suppose these circuits are now also computable efficiently. So, when we talk about NC1, we do not talk about how these circuits are obtained, we just say that if there exists a family, that is it, that is good enough for us. But how can we obtain such a family? So, now let us say if this family can be computed efficiently, then we come to this notion of uniformity, okay. And let us say if this family can be computed in log space, then we call it as log space uniform. So, what is log space uniform? So, log space uniform is the class of functions for which there is a NC1 circuit family, let's call it as Cn, so it's an infinite family such that there is a log space Turing machine that when given 0 to the power n as input outputs Cn. Okay. So, if you are given n as input in unary, so this is actually important, so n is not given in binary. So, if you are given n as input in unary, this log space Turing machine outputs Cn. So, what is a log space Turing machine? So, again just to make sure everybody understands the complete definition. So, a Turing machine of course is something that we all know. So, Turing machine is a model of computation where you have an input tape, you have finite set of states, and the machine can and there is a work tape as well, and now the machine can do some computation given an input and then accept the input or reject the input. Okay. So, now you can also think of a Turing machine with an output tape. Okay. So, suppose the Turing machine has an input tape from where it gets the input, it has a work tape on which it does its computation, and there is an output tape on which it produces the output. So, the input tape is a read only tape, you cannot use the input tape to write something or do any computation. The output tape is a write only tape, that is you can only write whatever bits you are computing or whatever bits you want to be there on the output, and you cannot read something from the output tape. And the work tape is both a read and write tape, so basically you can do anything on the work tape. And when we talk about log space, essentially it is the space of the work tape that we are concerned about. Okay. And the reason why we are only looking at the space of the work tape is because usually the input, of course the length of the input is n. Okay. So, everything is measured as a parameter of the number of bits on the input, which is n. So, when I say log, it is log of n. Okay. So, clearly the input tape will have linear size, it has size exactly equal to n. Okay, so, if I include the input tape in the space when I am counting my space, that is kind of not fair, because you might not need that much space in your actual computation. In your actual computation you might need much lesser space. Similarly, when I am looking at the output tape, maybe you are just outputting some stuff, but you do not actually use that for your computation. Okay. So, the output tape also can have size that is linear, quadratic, or any polynomial, but you are not actually reading from that tape, it is a write only tape. So, that is also not counted during the process of computation. Okay. So, if you have actually done a course on complexity theory, these things are quite these things are of course told over there, but I just want to give a brief idea. So, when I say log space Turing machine, it is a Turing machine with a input tape, output tape, and a work tape, and I am only looking at the space of the work tape as a function of the input size. Okay. So, any questions?
So, here this unary is taken in order to make the log space log of n.
Yes.
Because if it is binary, then the log space would be log n.
Yeah, exactly. What is the log space uniform NC1, and this is we will only be looking at NC1 for the next couple of lectures. So, that is why I have defined it in terms of NC1, but you can define log space uniform for any other circuit class as well, it is the same definition, similar definition. So, why are we talking about log space uniformity? Because essentially finally what we will show is that division is not just in NC1, but is actually it is in log space uniform NC1. Okay. So, not just there is a circuit family NC1 circuit family computing division, that circuit family can also be computed in log space. So, that is the that is the power of this theorem.
Like all the other problems are also in log space uniform.
So, depends. So, if you can actually compute that circuit given n in unary, if you can compute the circuit, then it is in log space. So, yeah, I think most of the problems that we have seen, they are in addition, multiplication, they are in log space uniform. Yeah. You can actually generate that circuit. Okay. And the important thing, so this also I had mentioned a couple of lectures back, and I want to mention it again because this fact we will be using quite frequently, is that so when I will, so when I am, let us say when I am given the input, okay. So when I say log space Turing machine, given n in unary of course, this Turing machine basically can compute anything. So how do I want to say this? So okay, so given let us say an input x, so let us say if I want to build an NC1 circuit and I am given some input x, as long as I am not looking at what that x is, okay, so what the individual bits of that x is, if I am let us say looking at some global parameter, or even if I am looking at n, I can use the power of log space to do any pre-computation. Okay. So, that pre-computation might not be in NC1, it might be in log space, but that is actually still good enough for us because that pre-computation does not look at the actual bits of the input. Okay. We will, if you are not very clear, we will discuss this again when I come to this. Okay. Let me carry on. So, this is log space uniform NC1. The next definition that I want to give is that of NC1 reduction. Okay. So, a function f is said to be NC1 reducible to a function g if there exists an NC1 circuit family computing f that in addition to the usual gates has oracle gates for G. Okay. So, we say that f so okay, so what do I mean by oracle gate for G? So, oracle gate for, so G is a function, okay, and G can be any function, okay, it can, let us say you can think of G as taking a string and outputting in some other string, it can be any function. So, an oracle gate for G is essentially a gate, okay, which takes as input some bits and it outputs, okay, f of that sorry G of those bits, okay. So, this you can think of as a G gate, okay. So, it is taking as input some bits and it is outputting, let us say it takes some y. So, this is let us say some y and it outputs the string g of y. Okay. So, this is what an oracle gate is. Now, we say that f reduces to g, NC1 reduces to g if there is an NC1 circuit which in addition to the AND, OR and NOT gates also has these oracle gates for g. So, at any point of time you can basically produce a string and you can query that is this computable in g or whatever, what is the output of g of this. Okay. Okay. So, our reduction, so when we say that these problems are equivalent, so our notion of equivalence would be with respect to NC1 reducibility. So, let us get started. So, first what we will show is that division reduces to powering. Okay. Where is? Circuit family computing f. So, it is a NC1 circuit family which is computing f, but in addition to the usual gates it also has oracle g gates. Okay. So, let us look at this thing and we can see this with respect to this. So, division is NC1 reducible to powering. So, essentially what we will show when we prove this theorem is that there is a NC1 circuit for division which in addition to AND or NOT gates, it has some gates for powering. Okay. So, there are some powering questions that we will ask and we will assume that we have those answers. Okay. That is essentially an application of this. Okay.